Closer. Okay. All right. Yeah. It's not respecting the distance, but okay. So today I want to show you something I played actually during the pandemic with. So it's a pandemic project. And it's about trying to generalize the whole story of alternating sign matrices, the Vertex model, and use of integrability to the case of a triangular lattice. Okay, so that's the thing. It's not more than that. But the fun thing is that it actually, the more you dig in this problem, the more you find wonders of several types. But one of them is of combinatorial type. And I stumbled on new objects. So here I made a sort of program for this talk. So after recalling things on the square lattice case, I will go to the triangular lattice case. And in particular, there's the question of what should you call domain wall boundary conditions when you're on the triangular lattice. So I'll explain a bit about that. And ASM is actually generalized into APM. I'm not going to tell you yet what it means, but that's one part of the story. The other part of the story was these magical relations between the counting of alternating sign matrices and other objects of combinatorics, like rhombus stylings of certain domains, right? And so in this case, by digging and brute force, I found an interesting tiling problem, which was enumerated by the same number as the configurations of this domain wall boundary condition ice. And I call it the holy Aztec square. So it's like an Aztec diamond, which you probably all know about. And then you punch a hole in the middle and you impose certain symmetry conditions. And then it's not quite square, but almost. And this object is actually giving you the same numbers. So I think from that point of view, it's interesting. And I'll show you how to prove this correspondence. Okay. And then there's more. Because there are many other ways of defining domain wall boundary conditions, I'll show you some of those other ways for which I found interesting conjectures. So there it's not proved. And it's a conjecture which also connects the counting to counting of domino tilings of other domains. So the main thing here is that we traded rhombus tilings for domino tilings, basically, by going from square lattice to triangular lattice. Okay, so I'll describe those combinatorial conjecture. And finally, I'll give you some more recent things I've been doing with other people on limit shape and the Arctic phenomenon for these new models. Okay, so combinatorially, it really boils down to these three sequences, which I've written down there. Okay, so you might even recognize some of them. All right, so I guess I could also pass these slides, but I just want to recall things about the 6 vertex. Okay, so it's ice in 2 dimension, H2O, so 2 H's are closer to an oxygen. You put the oxygen ions on the square lattice, and then you replace the data of a configuration by the dipolar momenta, which are just small arrows along the edges. And so you have oriented edges like this. And the fact that 2 hydrogens are closer to an oxygen is just the ice rule, that you have as many entering as outgoing arrows at each vertex. Okay. All right. On top of that, we're going to consider domains, which are square domains, on which we impose domain wall boundary conditions. The domain wall boundary condition is a boundary condition that imposes the existence of domain walls. So the best way is to just impose opposite directions of these arrows. So somewhere in between, they will have to change directions, and that will be a domain wall. Okay, so there's various ways of representing the configurations. So that's the first way by which I defined the whole thing. But you have 2 standard bijections. One is into what are called oscillating paths, right? So you're deciding on a basic in orientations of the vertices of your lattice, or the edges of your lattice. And then whenever you agree with it, we are going to paint the edge in red. And if you disagree, then you paint it, you don't paint it, okay? So then the 6 configurations here are just turned into those configurations, and you see very well that I can think of this as paths going from the northwest to southeast, right? And this vertex is a bit special. We still think of them as non-intersecting paths, but they share a vertex. So they just bounce against each other. That's what's called an oscillating path. Okay. And the last version is to just, again, look at this and realize that those vertices can be classified into two classes. There's those that transmit the arrows and those that reflect the arrows, right? So for the transmitters, we're going to replace the vertex by a number 0. And for the reflectors, depending on how you reflect, it will be a 1 or -1. And then you have, of course, a matrix n by n with 0s, 1s, and -1s with certain rules due to these reflection stories between the domain walls. And that will be alternating sign matrices. So this is the summary, right? So the three ways of looking at the same configuration, right? Either as alternating sign matrix or oscillating paths or 6 vertex. Okay? All right. So here is a small part of the world around these alternating sign matrices. So the left part we already discussed. The right part came a bit out of nowhere by simply looking at things that people had been able to calculate, right? And so these totally symmetric self-complementary plane partitions, which you can think of, you take a corner of the room and you pile up with cubes, right? And you impose, so looking at this it's a three-dimensional piling up, but you can look at its projection, which is two-dimensional, and then it looks like a rhombus tiling, okay? So if you rhombus tile a regular hexagon of size 2n, 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 and demand that this object be as symmetric as possible, then you get these totally symmetric self-complementary plane partitions, which are enumerated by enumeration of configurations of their fundamental domain, which is 1/12 of the hexagon, and they're called TSS-CPP. Okay. Another object which I ask you to concentrate on, because this is really the one I'm going to generalize here, is a sort of hexagon, but not quite, because it has edges n, n+2, n, n+2 alternating, and it has a hole in the middle, a small triangle of size 2. Okay, so this thing is actually in bijection with an object introduced by Andrews, which are called descending plane partitions. And so a descending plane partition is in bijection with rhombus tilings of this object in such a way that there's a 2π/3 rotational symmetry. Okay, so you tile an object with a hole and you impose a symmetry, right? Okay, and then the number, forgot the number, but the number you can compute in various ways and identify it. So the great thing is that you have a number, but the sorry thing is that you don't have bijections, right? They're all counted by the same number, but there's no bijection, and it's still open. Okay, so behind this is, of course, the integrability. So I'm going to be quick here. So you can attach to configurations weights, actually, which are just Boltzmann weights. So you define local weights, and then the product of local weights of any given configurations give you the weight of the configuration. You can do probability if you want, right? Think of those weights if they're positive as probability weights and play with that. So the tool behind that is the R matrix, right? And okay, I don't want to enter into that detail. I think the only thing you have to know is that basically this description of the weights as intersections of two lines are such that they obey invariance under moving lines around, which is called the Yang-Baxter equation if you go down to the definition of those weights, but which just means this picture. Okay, so you can move lines around. That's the thing you have to remember. Now, here is the solution for the entries of this R matrix. So basically, it tells you what the weights are in terms of parameters which are carried by each lines, which are spectral parameters. And you have these three numbers, A, B, and C, functions of Z and W. And there's a parameter Q, which is a quantum parameter that you can attach to each of those models. So you have a 6 vertex model with quantum parameter Q and spectral parameters Z and W. Now, if you're on a square grid, you can choose any spectral parameters you like horizontally and vertically. So it's like 2n different parameters plus a Q. So that's 2n plus 1 parameters for each of your models. Okay, and then for the most general configurations and some other configurations, the partition function of that model, depending on all these parameters, Z's and W's and Q, is actually given by the Isergin-Korepin determinant. And the amusing thing is that this part here, of which you have to take the determinant, so this is a product of a bunch of numbers, not very interesting, but this is more interesting. It's a determinant, and the argument of a determinant is precisely the potential that you saw already in Jules Lamer's talk. Okay. All right. So the proof of this, of course, relies integrally on integrability. So the freedom of moving lines, which allows to prove symmetries of this object. And then there's another property, which is basically the fact that you can get rid of one of the weights if you fine tune the spectral parameters, and that gives you a recursion relation. So recursion relations plus symmetries determines the whole thing. I think this morning there was a discussion around this thing. Okay, so enough for the recalling old stuff. So now the new stuff. So we switch to a triangular lattice, and because I'm lazy and I can't write triangular, I write it on a square lattice. Okay, so square lattice with one diagonal. The ice rule was that I painted arrows on each edges, right? And at each vertex, there should be as many entering as outgoing. So that's still true, but now it's free, right? So the number, earlier I had two choices among 4, that was 6 vertices. Now 3 choices among 6, that's 20. Okay, that's where the 20 vertex comes from. And this thing was studied in depth by Kelland, who was doing his thesis with Baxter, I think. So quite a while ago. And it was kind of discarded as not so interesting because the free energy kind of splits into free energies of 6 vertex models. But you will see that this is a key to what we're doing. Okay, so just like I showed you for the 6 vertex, you can replace the pictures with orientations of edges with pictures with oscillating paths. But now my paths can have 3 types of steps: horizontal, vertical, and also diagonal. And if you zoom in here, you will see that I have a ménage à trois, right? I have 3 paths which are non-intersecting, but that all share the same vertex. So there's multiple kissing involved, right? Okay. All right, so what about boundary conditions? Well, the sort of lazy way of doing this is to say, okay, I drew the thing on a square lattice, so why not try to imitate the boundary conditions of a 6 vertex model? So that's exactly what I did. And so these are entering arrows on all the horizontal and diagonal edges on the west and east, and outgoing arrows on north and south, okay? So that's one. Now you realize very quickly that these guys is not clear whether they belong to the west or to the north, right? So you have 2 choices. So it gives you these 2 choices. But then, of course, if you rotate by pi the bottom guy, you end up with the top guy. So they're the same, in fact. Okay, but here I'm representing oscillating path configurations for those guys. All right. Now another type of boundary condition, which is less constraining in a sense, but still induces the existence of domain walls, is to take every other guy entering, right, on the west and east. So all the horizontal guys, if you want, enter. And here all the vertical guys exit. But the rest, all the diagonal, they just all go in the same direction, right? Okay. So it's a completely different model, in fact. All right. Now you can play with transfer matrices and count the configurations, and for you find these 2 sequences for domain wall 1, 2 and domain wall 3. Okay. All right. So here are, for instance, the 23 here configurations for size 3, domain wall boundary conditions 1. Okay. Bon. Okay. So now I change completely. Yes. Yes. You will see. Just be patient. But yes, answer is yes. So now I change completely I mean, it's a different thing, right? And I'm looking at this particular domain. So let me try to describe this domain in a better way. So I'm looking at rectangles that look like Aztec diamonds, right? But which have a little defect here, right? Okay. I take 4 of them and then I glue them by pushing them together. And what I get is almost a square, right? But with a sort of defect here, 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 and here. And then a hole in the middle, which has the shape of a cross, right? Okay, nothing religious about this, but for some reason, I call it the holy, because it has a hole, Aztec square, right? And now what I impose on top of that, because I'm trying to imitate what I showed you was the case for descending plane partitions, but there was this Z3 symmetry, right? Rotational symmetry. So now the natural symmetry would be a Z4, right? So pi over 2, right? A rotational symmetry in my configurations, which will be pi over 2. And the natural object with which to tile this is the dominoes, right? 2 by 1. Okay, so that's a problem, okay? Count the tiling, the domino tilings of this. So there's a quite simple way. First of all, you restrict yourself to a fundamental domain and realize that this rotational symmetry just means you're on a cone, right? So it's like an ice cone, right? Which you've seen already in Florence, so it's perfect. But it's an unlucky ice cone because it has this hole here, right? And so when you close the ice cone, you end up with a nasty hole in the bottom, right? So you better eat your ice cream very quickly. Otherwise, something bad is going to happen, okay? All right, so we're on this cone. And we're, of course, going to use the standard dictionary between dominoes and paths, right? And those paths will have exactly 3 types of edges. So they are same types of paths I showed you before, horizontal, vertical, diagonal. But this time, because it's a tiling problem, by definition, those paths will be non-intersecting, really, no kissing there, so serious paths, okay? So, and there is this forbidden zone here because there was a cross in the middle, okay? So you can count that by using Gesell-Vienot, lattice fermions, whatever you like. And the answer is a determinant. So actually, it's a combination of Gesell-Vienot and Cauchy-Binet, which is telling you that the determinant of the identity plus a matrix is the sum of all the diagonal minors, right? And these diagonal minors by Gesell-Vienot are really minors of a matrix that codes the tiling, in which the entries that you choose in your minor correspond to these arrival points and starting points of the paths. But we're on this ice cone, right? So, so they are the same. So these are diagonal minors, and that's why this thing works, okay? So here I chose to represent the matrix via its generating function. So you generate the element ij of a matrix, right? By a function of z and w, and say it's the coefficient of zi wj, okay? So it's an infinite matrix a priori, but you're only taking a finite truncation of it. So it's always the same matrix that does the job for the counting that you want to do, but it's just the size that tells you which number is going to be obtained. And just to convince you that this is not completely crazy, the 23 I showed you before corresponds to the case n equals 3. So you replace, you expand this to order 3, right? And you find indeed that this determinant is 23. So it works. It works for that guy. Now, why would it work for the general guy? So these are just sample configurations. These are the 23 tilings, right? And I put in red the fundamental domain. Okay, so what you see, okay. So, and these were the 23 of before, right? If you can find me a bijection between these guys and those guys, I would be really happy. Okay, so now back to my 20 vertex and try to show that these things have to do with each other. So here the idea will be simple. So to answer your question, if this will use the integrable structure of some underlying 6 vertex model to define weights for the 20 vertex, which is something that Kellan did in his thesis, by the way, then deform line arrangements and show that it boils down to a single 6 vertex, in fact. So you can actually count things. And once you're in 6 vertex territory, you have the determinant of Vizergin-Korepin, you can play and get almost everything you want. Okay, so that's the idea. So here is exactly what we're doing. These 6-valent intersection and triple intersections of lines are not nice. So what we do is we resolve them by pushing slightly the diagonal lines. Okay, and so once we push the diagonal lines, we create these triangles here, and we can decide to orient the edges of those triangles in such a way that the ice rule is satisfied at each vertex of the triangle. Okay. Now you might have you always have at least one solution. There might be two actually. So it's not 1-to-1, right? But possibly 1-to-2. But somehow we don't care, because once we're going to have put all the weights in there, we're going to get weights for the 20 vertex model in terms of the weights for the 6 vertex model. So we'll have weights, okay? And those weights we will impose that they're the same if we push the lines down or push the lines up, right? So it's sort of Young-Baxter equation again. So here is how it works. I have my 3 sublattice ice rule vertices, right? Which are the sublattice 1, 2, and 3 on this picture. Right, so I have a collection of Boltzmann weights for these 3 models. I define the weights of 6-valent guys as the sum of the weights summed also over all the possible inner configurations, right? So sometimes it gives me 2 terms instead of 1, but here I'm comparing this with a case when I take the diagonal up, and there is only 1 term corresponding, right? So it means that there are some relations between those guys, right? And this is just another way of writing Young-Baxter, right? So anyway, that defines for you unambiguously weights for the 20 vertex model, which will have this really nice property that you can move lines around again, right? But now you have 3 sets of lines that you can move around. So these are the weights expressed in terms of oscillating Schroeder paths, right? These paths with horizontal, vertical, and diagonal edges. And these are just the values of 6 different weights corresponding to the 6 different boxes here, right? Which you inherit from the 6 vertex models on the 3 sublattices. And here are the ways the spectral parameters are just expressed, right? In terms of some parameters, lambda, mu, eta, and so Q is exponential I eta. So if you want to be in the so-called disordered phase, which will come from disordered phase of the 6 vertex, you have to take all these lambda, mu, eta, etc., to be real. Okay. So the remark here is that you can also get the uniform weights. You want to all the omega to be 1, and there is such a way. It's a bit strange, but you need pi over 8. So it means that Q is a 16th root of unity, but sometimes people use Q squared in terms of instead of Q. So it's 8th root of unity in that notation. Okay. So it's not the usual Razumov-Stroganov, whatever point, which is cubic root of unity, right? Here it's 8th root of unity. All right. And now these uniform 20 vertex weights, they actually correspond to non-uniform weights on the 1, 2, 3 sublattices. And look, it's even different on 1 than it's on 2 and 3. Okay, so this is an important thing. And this will reappear. So be patient. So now let me show you how, starting from the 20 vertex configurations on this domain wall case, we can actually boil down to a 6 vertex. So what you do is you pull all the lines. Okay, you can do that. And now you're going to move the diagonals. So the idea is to move the diagonals of the upper half to the top and the diagonals of the lower half to the bottom, right? So the red diagonals I pushed down and the blue diagonals I push up. Okay, so that gives me this. All right, so why is it interesting? It's interesting because of the boundary conditions. So let me go here, for instance. You remember on the east side, everybody was entering, right? So in particular, these 2 guys are entering, but there's the ice rule, right? So these guys are completely enslaved, right? They have no choice, they have to exit. But then the next guy also has everybody entering. So these guys also have to exit, but then it propagates, right? So all these configurations of edges in this entire domain, they're all completely frozen, right? And it's true also here, here, here. So what you end up with at the end of the day is a bunch of numbers that multiply the center, which is the partition function of 6 vertex. That's it. So this is how you go from 20 to 6. Okay, and so only the sublattice 1 subsists. Okay, so here is the theorem. Okay, in the case where you're uniform, right, all the weights equal to 1, I showed you that ABC for the sublattice 1 should be 1 square root of 2, 1. Okay, so these configurations with these weights, they count something actually, right? So this is kind of a new thing. So I just want to show you that one should always observe nature because all the answers are there. Okay, so this is not a Kagome lattice, but it's a lattice of Kagome. So Kagome is this delicious beverage which you find in Japan, and this was in a grocery store, and they form a nice lattice. Okay, and now if you zoom on the ingredients, there's 20 fruits and 6 vegetables. Amazing, huh? Okay. So, or vice versa. Sorry. I'm sorry. I'm thinking as a person who doesn't like too much vegetables, but okay, you're right. 20. So it's not so well to a French. It's not so good, but okay, it's still a delicious beverage. Okay. All right. So here is the illustration of this theorem with the square root of 2 weight on B-type edges. A B-type configuration is whenever a path goes straight, right? So I put a small black cross here whenever the path goes straight. So I get a square root of 2 here and here. So it's a weight 2. So now I'm just enumerating the 6 vertex configurations. So for instance, the 7 alternating sign matrices or 7 oscillating paths, right? But each of them receives a certain weight, okay? And now I sum all these weights, and of course I find my favorite number, 23. Okay. All right, so now how do I connect this with what I computed before, the holy Aztec thing, right? It was a determinant, right? So we have a Nizargin-Korepin determinant. So we just have to sit down, figure out which limits of that determinant we should take, right? And okay, it's work, but it's doable. And at the end of the day, you find the exact same determinant, okay? So it works. All right, so far so good for the things we understand. So now what we don't understand. So I told you there's this other type of boundary conditions, right? Where you take every other arrow oriented in now. And these are the numbers here. So you look at the, OEIS, right? The integer sequences, and you find that this number appears in the actually domino tilings of a 2n by 2n square. Okay, but it doesn't appear directly, it's the square of it, right? But then there's all sorts of interesting developments around domino tilings made by people like Chuku, for instance, who showed you that whenever you have a 2 to the n times something, it just means something with a symmetry, okay? And so what eventually Parter found quite a few years later is that this Bn itself counts something like half the square, right? But you have to cut your square in a very specific way with steps of 2 like this. So the domino tilings of this half square, if you want, or triangle, if you want to call it, is given by the Temperley-Fisher formula as a product of eigenvalues of Laplacian. And okay, so it's not obvious that these things are integers, but they are, and you find this sequence. So it seems to be the same, okay? So here's the conjecture, right? The configurations of domain boundary condition 3 would be the domino tilings of this triangle, Parter triangle. Okay. Now, one conjecture is not enough. So here is a bunch of them. So now we modify a little bit our boundary conditions. We sort of extend the square into a rectangle in which we impose nothing on the bottom part here, right? And so we have the same number of starting paths and ending paths, right? And all the rest is unoccupied. So I call it a pentagon of triangular eyes, right? Because it's a pentagon now, my domain. And now it depends on a new parameter k, right? Which is just an integer. Okay. Now, what can you do with a triangle of before? What you could do is just raise the roof above it. Okay. So here is the roof that I'm raising, and I'm raising it in such a way that I end up with something like an Aztec diamond shape. Okay. So it's a bit ad hoc, but here is the conjecture that the pentagons of ice are actually enumerated by the same numbers as the raised roof triangles. So domino tiling on this side and 20 vertex configuration on that side. So that's open, okay? Open except for one case, but it's an open conjecture. Yes? For the usual, there is no analog. No known analog. So maybe one should go back and try to figure it out. Yes. Yeah, good question. No, same thing as before. I'm just piling up on impossible bijections, basically, right? So I know that the numbers are the same, and I have no idea how to cook up a bijection. But I'll show you the closest thing to a bijection I can come up with. Okay. All right. So this is the one case I know how to do. So it's by pushing. If you push the roof to infinity, basically. So no more roof here. And then if you go down as much as you can, you will have a quadrangle instead of a pentagon, right? So this is this situation. On the left, the 20 vertex quadrangle. On the right, the raised top Aztec triangle. And they're enumerated by my third sequence, which is 1, 4, 60, 3, 3, 2, 8. Okay. And that I can prove. And how do I prove it? Same way. So it's really, there's only one way of proving things. So first of all, the theorem. So these numbers are the same, and they're actually expressed as a simple determinant. Again, I like to show the determinants, or the matrix of which you take the determinant as an infinite matrix with its generating function for its elements. Okay, so UV are just the generating parameters. Now there's a conjecture that the number you get out of there is given by this. Now, this is an interesting conjecture because this number looks very much like the number of alternating sign matrices, in which the role played by 3 is now played by 4. There is also this term in front, which is a bit mysterious, but okay, it's necessary for the whole thing to be an integer, so it has some natural reason to be there. Okay, so that's another conjecture, but this is proved. So let me show you very quickly the proof. Well, it's the same thing. You start from this guy, okay, with its spectral parameters, and then you start moving whatever lines you can move according to the rules that I explained before. So you're going to move a certain number of diagonal lines up, a certain number of horizontal lines down. Realize that all these guys are frozen for the exact same reasons as before. Then end up with a guy like this, and here again, those guys are all frozen. And so in the end, you end up with these types of configurations. So you enter horizontally on the east, you exit north and south, and then on the west, you have these U-turns, right? So it's called the U-turn boundary condition, introduced by Kuperberg, also Tsuchiya considered it, right? And it's also a determinant, but with a reflection. So it's like the potential of Jules, but with a reflection in it. Okay. So because you can do that, you can express a determinant on one side, determinant on the other side, identify them. So it works. All right, so now in the last minutes, I would like to discuss the Arctic phenomenon for all these models. So instead of, of words, I think a picture is much better. So this is a very large configuration, typical configuration of a 20 vertex model in the former boundary condition, the domain wall 1, right? The first one I discussed. And so you can see, or maybe you don't see, but so here you see it's empty, okay? So I call this a frozen phase. It's a frozen empty phase, empty to nothing, okay? All right, this is another frozen phase in which I have only parallel lines, okay? This is another frozen phase. This is another, it's completely full, right? This is another, and this is another. So I have these, all these frozen phases. And then in the middle, so probably you can guess with me that there's a sort of limit curve which looks a bit like this, right? Like a coffee bean, right? Which would be very adapted also for Florence. So, okay, so this is just the illustration of a more general thing, which is this Arctic phenomenon, which seems to always appear when you constrain sufficiently the boundary conditions that the model becomes interesting, right? So this domain wall kind of always carries such phenomena with it, okay? So now I'm going to use the tangent method, which was invented by Filippo and Andreas Portiello, who was here last week, around 2016, pre-pandemic. And which goes as follows. So you have a soup of paths, right, which are attached at their ends here and here, right? And then it's a soup of paths. And clearly, the boundary of an empty frozen domain is going to be given by the outermost path, okay? So what you do is you detach this top path from the rest, and you use it to learn something about the other paths, right? So as far as the path is far away from the other guys, it doesn't disturb them. And when it's close to them, it's actually part of them. So it doesn't disturb them either, right? So it really reveals the structure of those paths. So asymptotically, it gives you something like this. So you expect a certain curve here, asymptotic curve. And now, if you can figure out the most likely exit point of this path here, right, which is now attached somewhere else, so it has to exit, right? Then you can draw the line that joins the most likely exit point to the new endpoint, and that line is going to be tangent to the Arctic curve. Okay, actually, it has to be a line because a path left to its own devices follows a geodesic, and I have no background, so the geodesics are lines. Okay, but you could put a background, for instance, a weight related to the area under the paths, and then the geodesics would be curved, but you can still apply this method. So here is how the method would work for 6 vertex, right? So you just moved the endpoint, which was here to there, right, to this green dot, okay? And now you want to find the most likely position of this exit point. So you have 2 partition functions you have to compute, the pink and the blue, okay? So the pink is something like what you would get from Isargin-Korepin type determinant, except that now you move this guy here. So it means that you have to keep a spectral parameter different from the others, okay? That's how you get that. This is very simple. It's just a single path with the weights of a 6 vertex model, right? So you can compute this and then estimate by some saddle point approximation. And then you find which k given L is going to be the most likely. So you get a parametric family of lines, and then the envelope will be the Arctic curve. So this is the same for domain wall boundary condition 1, and this would be the same for my quadrangle of Arctic ice. So all the same type of approaches. Okay, so how do you compute actually these asymptotics which allow you to find these most likely exit points? Well, you use the fact that these are given by determinants, okay, and you use the Lewis-Carroll, Denano-Jacobi identity on minors of any given matrix, and that gives you relations of this form. So that's for the partition function itself, okay, partition function in which you have all vertical and all horizontal spectral parameters fixed, and you end up with a free energy which satisfies the 2D Liouville equation, and with boundaries you can fix everything. And the other one is about one-point function. You remember I needed to be able to fix the exit point somewhere along this line. So I just change the value of the spectral parameter on the right here. And by doing that, using the same equation, I get now a relation between the one-point function h and the partition function, which you can also write down in the limit. And then you just have to integrate to get this unknown function psi in terms of the function f. Okay, so it's quite systematic and easy. And once you have that, you sit down, you compute your saddle point, etc., and you find your Arctic curve as the envelope. Okay, so it gives you actually, strictly speaking, only one portion of Arctic curve, and you have to repeat this with other families of paths to get all the others. Okay, so there's more work than what I show, but. So these are simulations which confirm. So this is really the plot of a curve predicted by this tangent method. And this is the picture, right? So, I mean, it's very convincing, I think. All right. So now, of course, I showed you a family of 7 different weights, right, for the 20 vertex model. So now you can play with those weights. You're going to land on some 6 vertex with different weights also, but you can repeat this exactly the same approach and find these Arctic curves. And well, the simulations really are really convincing, I think. Okay, now you can play the same thing with Aztec, Holy Aztec square. Why? Because we showed that the determinants were the same, but it's even better than that. The one-point functions are the same. So you can apply the tangent method also to the tiling problem, okay? And you find a curve which is of degree 10 and which has this nice Z4 symmetry, right, for the domino tiling. So here you don't see it, but there's a holy cross in the middle, right? Okay. And now I can put everybody on the same picture. And here is something really remarkable. There's a common branch to the Arctic curve for the domino tiling and for the 20 vertex. So that's what I call the closest to a bijection I can be, because the separation of phases seem to be the same. So there's really some stronger connection between these two problems. And what happens, in fact, is that if I take this branch, which was strictly speaking what you get by applying the tangent method to the domain I showed you, right? And you take its analytic continuation, you find something which has a Z4 symmetry like this. That's crazy because you started with a problem that doesn't have any Z4 symmetry, right? But it's somehow telling you that you should have guessed that there was a model for which an analytic Arctic curve would have this Z4 symmetry. And we found that model. It's this Holy Aztec square, right? So it's all quite coherent. And what happened is that if you take the analytic continuation, which is here, and apply a simple shear, you find the actual branch, which is here. Okay, so it's even better than that. In the uniform case, there's a sort of shear phenomenon which allows you to get Arctic curves for these interacting fermions as shears applied to algebraic Arctic curves, right? They're non-algebraic, but they're piecewise algebraic, and somehow each piece is kind of a shear of the same analytic continuation. And the same thing actually happens for alternating sign matrices and descending plane partitions. Imagine my hexagon of earlier with a little triangle in the middle, which of course boils down to 0 in the asymptotics. Again, the Arctic curve for the alternating sign matrices is made of 4 pieces, right? So, and each piece is a piece of ellipse. So if I draw the ellipse, I find actually the Arctic curve of a rhombus tiling problem, which is the descending plane partitions, okay? And then again, the same shear applied to the analytic continuation gives me the new piece of curve. That's something that Andrea and Filippo had noticed, but I think we have a better way of understanding it now from having gone to a 20 vertex model. And here is the explanation. So you start with the domain wall boundary condition 1 problem, right? And now you're looking, you're trying to figure out what the second piece of Arctic curve should be, okay? So to do that, it should be the separation between 2 faces. And we like separations with empty faces. So what we do is apply the vertical flip, which means that each vertical edge, when it's carrying a step of paths, we are going to remove that step. And whenever it's empty, we are going to put a step of paths. Right, so we flip, we invert, if you want, the occupation numbers of the vertical lines. So clearly here, all these guys enter and then they exit on both sides. So somewhere in the middle, there should be an exit to the top, right? And also an exit to the bottom, by the way. So we concentrate on that exit to the top, and we figured out that by applying a shear, we could recover the same geometry for our weights as the original geometry for 20 vertex model, except that it's upside down, okay? So now we can apply the tangent method to this new picture, which has the good weights, right? But upside down. So here also, I'm going to use weights upside down. Also, the contact point to the edge here is not K like it was before, but n minus K, right? I have to interpret it in a slightly different way. So my paths actually are moved on top instead of on bottom, okay? So things change a little bit. But in the end of the day, if I want to go back to the actual curve, I have to apply the inverse of the shear, right? So the inverse of a shear is a shear also, right? And that's where this shear is coming from, okay? Well, I'm trying to give you, okay, this is not very precise, but this is what happens. Okay, now open problems. In this case, I can also compute the Arctic curve, right? So same thing, this guy is a shear of the other. So, but I have no idea how the curve continues. And of course, the guess is that it should continue something like this, okay? But so far, I haven't been able to figure out what happens. What's funny is that if you take the analytic continuation, so this is my quadrangle of 20 vertex, right? The second problem I was able to solve, and I take its analytic continuation, guess what? I end up with the same curve with symmetry Z4, okay? So this is kind of strange. And what happens is that the non-bijection I found was between the tilings of this raised roofed triangle and this 20 vertex on quadrangle. I can put them together on the same picture. And again, they have a common part of Arctic curve. So one of them is a domino tiling problem. So the Arctic curve continues with the analytic continuation. But this one takes the analytic continuation and uses a shear to finish, right? So I have these two, there's a piece that is common between the two problems, and then it's kind of different on both sides. So that's as close to a bijection I can get. All right. So this is the conclusion. I hope I convinced you that we have interesting combinatorics hidden in there. There's this Arctic phenomenon. So all these cases have one, okay? And using this tangent method, which for those cases is still not rigorous, right? Because Amol hasn't done the job yet, but I have hopes. And we found connections to both the 6 vertex and the U-turn 6 vertex, right? So there might be even more objects, which we know that there's more versions of 6 vertex, right? In Cooperberg's paper, Under One Roof, he has all these other versions of 6 vertex with different domain wall boundary conditions, etc. So I have kind of hopes that one can also describe analogous objects with 20 vertex. There's this question of non-analyticity of the Arctic curve, which is really seems to be a landmark of the fact that it's interacting fermions as opposed to non-interacting fermion when you look at non-intersecting paths. And one can ask these last two questions. Could one relate this to loop models in any way so that we could come up with the Razumov-Stroganov part, which is still missing? Okay, so that's a question. And the other question, I have a few hints already, which is, can we classify actually these domain wall boundary conditions, like find the good ones, right? So I found another one by asking myself this question. So there's this guy. So now I put them back on the triangular lattice, just to show you what it looks like. So these ones we've seen already, these. But now I claim that if I, on the west boundary, the n first are entering horizontally and the n last are exiting diagonally like this, I still have a solvable problem. So these are the configurations that correspond to it. It depends whether it's even or odd, because you have to know what you do with the central guy, okay? So it's not, but the remarkable thing is that the counting, you can prove, is again the same as counting in W boundary condition 1, up to a power of 2, which looks very much like the power of 2 we've seen before, and which looks also very much like the partition function of Aztec diamond itself, okay? So there's something fun going on here. And you can even figure out Arctic curves. So this is an artistic version because it's not all proved, but there would be, again, all these frozen configurations, right? Frozen phases separated by this liquid, this curve, which encircles the liquid part, okay? So again, in an interacting fermion case. More open questions. There's a really fun one here. If you calculate the Arctic curve by the tangent method, in this triangular case and look at this analytic continuation, right? You find this curve, which looks to me like it has to do with a domain that I drew around, right? So this domain, if you look at it in the right way, you can think of two Aztec diamonds eating each other, right? Like in a Pac-Man or something. So maybe there's still some kind of hidden model in there, but I have no idea. Okay. All right. Grazie molto.
Thanks. So, questions?
In your Arctic curves or the limit shapes, you have cusps. Do you know what are the power laws which describe those cusps?
So for the time being, I just
universal?
computing them. So I don't know yet about the fluctuations around those.
No, not the fluctuations, just how does it approach?
Oh, it approach. Okay, so let me show you some pictures. It's quite nice. It's okay. So here I think there's a line that goes to the 1/4 of this, right? So if you take the line that goes to 1/4, it's given by this cusp, the tangent at this cusp, for instance. So the tangents at the cusps are quite nice, right? In the other case, let me try to.
No, I think it's.
Did you want this one, for instance?
No, I think I am asking a much more simple question. It's just when you have a cusp.
Yes.
You have like a parameter which goes to the cusp.
Yes.
And how like x the width depends on this parameter. Is it known like because like if I take the only example which I know, which is like emptiness formation, it's an asteroid like 2/3.
But again, you're asking about fluctuations, right? Here, I'm giving you the actual formula for the curve. So, okay, so I didn't look at it, but there's an explicit formula for the curve. So one can, it's very easy to compute. But
my question isn't it universal because they, I mean.
Okay. So you're looking for universalities. I understand. Okay. So presumably the universalities,
Have you started doing this 20 vertices on the 3D cubic lattice? Is it
on which lattice? I'm sorry.
3D cubic lattice.
Oh, cubic lattice.
It's also 20 vertices, right?
But cubic means 3-dimensional?
Yes.
Oh, wow.
Well, is
3
there
dimensions?
Any fundamental?
Okay, I didn't try. Answer is no, I didn't try. I didn't dare, actually. Right. So, but
you don't know. You don't have any good reason that it wouldn't work, because there you can also resolve the vertices into pairs of force. I guess.
I have a hard time even figure out how things would generalize, right? So here I'm using a tangent method, so it would be a tangent plane method or something. Determinants, do you still have determinants? I'm not sure you would. Integrability, how would it manifest itself?
Looking at this, how you shifted these lines so
that
they come in 6 vertices. I think that you can, at least that you can also do in cubic.
So there are transformations, you're saying.
Yeah. And I think it's also fine to define domain wall boundary conditions.
Oh, we should definitely discuss them.
Yeah, let's do that later. Thanks.
So you have phases, frozen phase, and then liquid phase.
Yeah.
Do you have?
No, the other types of phases you would get if you had some periodicity in the definition of the weights, right?
Yes.
And we don't have that.
Okay.
Right. And I think it's very hard, even for the 6 vertex, right?
Yeah,
it's not known.
Yeah.
But of course, for the tilings, now there's plenty of work on that. Yeah.
Okay, thank you.
Ah, yes. I think so. Yeah. Yeah. So yeah. Okay. So, but from my point of view, it would be like going in a different direction, right? Yeah. Right. Right. I mean, I don't have any candidates. Yes. Exactly.
Oh, sorry.
So Philippe, so in the usual 6-vertex model, there was a second case when we had bijection with tilings. So at free fermion point, there was with domino tilings.
Yes.
Is there some free fermion point in your model where you have bijection with something?
So you mean the 2 enumeration? It was the 2 enumeration, right? So that means in my terms, it means the A was equal to square root of the C was equal to square root of 2, and A and B are equal to 1, right? So it's the vertex which carries the -1s in the alternating sign matrices, which is counted twice somehow, right? So in this case, you're asking in general perhaps about free fermion versions, right? So free fermion is actually my parameter eta equals to pi over 4. So Q is e to the I pi over 4, right? And this corresponds to free fermion points of the 3 different 6-vertex models that build up the weights, right? And in that case, of course, you expect the Arctic curves, for instance, to be analytic, okay? So you can fill the blanks. That's how I filled the blanks in the last picture, by the way. Okay.
But is there some nice tiling model? Like is there some new type of tilings?
You could repeat the Spohn-Ferrari thing, right? But I wouldn't say it's nice. It's what it is. It was nice in Spohn-Ferrari, but here, I don't know. But yes, you could do that.
But you have access to a microphone yourself. You don't need me.
Sorry, yes, I really appreciated your explanation of the shear phenomena, your picture. I was not aware of it. And of course, I mean, I suppose you tried also for the ASM versus free fermion case. You have a similar one and it works in more or less in the same way, right?
Mm-hmm.
Okay.
Mm-hmm.
So.
Yeah, no, there is something fundamental about it. The bizarre thing is that it makes perfect sense on the triangular lattice, but on square lattice, you don't see where it comes from, right? So it's only in the 20-vertex version that you understand where this shear is coming from. It's a bit strange. So I think it suggests that maybe one should look at the ASM or whatever other cases of 6-vertex with these different kinds of geometry or weights, or I'm not sure exactly how to say that. But it seems to me that the triangular lattice has added some information that allowed to explain this phenomenon, right? Okay, so it's a question.
Okay, I think there's one more. Say a last question, maybe.
So, what understanding do you have between the connection of the connection? Sorry, between the free fermions and the analyticity of the Arctic curve?
Well, like I said, it's kind of a common or folkloric knowledge that the free fermion cases always have analytic Arctic curves, right? And it's more, yeah, it's proved, right? It's proved. But the rest, why would it be only analytic by piece, right? Or algebraic by piece? I don't think there's an understanding of that. Huh? Yes. So if you, but the idea is that you should be capable at the free fermion points to change, to redefine your model or find a bijection to a model that you can describe, say, with non-intersecting paths or something, like Spohn and Ferrari did at this particular point of alternating sign matrices. Okay, so maybe it hasn't been done in detail. I don't know. Do you know, Filippo? Well, the other cases of free fermion in general, huh? But right, but it's asking for proof here. Huh? It's a mathematician. Yeah. No, no. No, no, no. You should be able to find connection without interaction. That's the point about free fermion.
As soon as you put some interaction, in principle, you destroy the blank.
But to be honest, I think the answer to your question is no. One doesn't know exactly how to make this work, right? One believes, but right? You don't have really a bijection between an arbitrary free fermion point of 6 vertex. That's right. That's. But maybe it's actually an interesting question. Yeah.
I noticed there are 3 Philippes discussing.
Oh, by the way, I have to mention that I stole his students a little bit, and he collaborated with us. Brian Debin collaborated with us with Emmanuel Guiter on this problem of 20 vertex.
Yes, 3. Yes, yes, exactly. 3, and 3 was also maybe on the Kagome thing. Anyway, so maybe we should now thank Philippe again.
Thank you.